Good morning. Good morning. Hope all is well. Hope everyone's doing all right. Sorry for running a few minutes behind. Trying to take care of some stuff. Got caught up in a little bit of an emergency, but yeah, that's pretty much what happened. All right, giving everybody a chance. Looks like everybody's in here. Okay, so hold on a second. Sorry about that. Had to sneeze. All right, so trying to map out what we're gonna do today. All right, so no, I said I was gonna at least do 5-1 today. Don't forget, next class Monday, we don't have class because it's a celebration of Juneteenth, so we are off Monday. So that's why we most definitely have to do at least one section today, even though we just close out chapter 4. But with that being said, did anybody have any questions on anything? Anybody trying to think it stuff? I meant to post, even though you have access to your test review, I didn't post your actual test for test 2. So I'll do that once we get out of this class. So forgot about doing that, but yeah. Any questions? Everybody good? Everybody straight?
When is test 2 due?
8/5, August 5th. Yep.
Okay, thank you.
Yep, no problem. When was the last recording for last class? Oh, we posted. If I can find time to do it today, I'll do it. Since you're asking, I'm assuming you're asking because you want it as soon as possible. So if I can find time today to do it, I'll do it. If not, tomorrow. Yeah, no problem. I just been normally I try to get it done on a Thursday or Friday. Just that things have been kind of off tilt for me. Trying to move, find a place to live, all that good stuff like that. So just things been a little hectic on my end, but try to get them done by Thursday or Friday. But I'll try to do that this evening since you are requesting it. All right, so see that no one has any questions. Remember, every day is opportunity for questions, and don't forget, I have office hours, and if you can't make office hours, always feel free to hit me up, and I will, see if I can accommodate you at another time. Monday, I keep saying Monday. Wednesday, I'll open the floor once more. I'll see if anybody have any questions, and then if not, we'll continue on in chapter 5. Okay, so today 5-1 probability rules. So starting with the definition of probability is the measure of the likelihood of a random phenomenon or chance behavior occurring. All right, can I scroll up? All right, then we have the law of large numbers. It says as the number of repetitions of probability experiment increases, the proportion with which a certain outcome is observed gets closer to the probability of the outcome. Oh, somebody says in the chat. Oh yeah, no problem. No problem at all. If I scroll up and somebody's still copying, always feel free to mention it. Let me know, type in the chat. So I can scroll back down. All right, so the next thing is experiment, and that's going to be any process with uncertain results that can be repeated. Simple example of that is flipping a coin. We're done with black. Mhm. And then your sample space is the collection of all possible outcomes of an experiment that's usually denoted by S. And in the example of flipping a coin, heads and tails would be the sample space. Those are all of your possible outcomes of flipping a coin. All right, everybody done with experiment? All right, so then your event is going to be any collection of outcomes from the sample space. So an example, for example, if I want to know what's the probability of landing tails, tails would be my event. Yeah, tails would be my event, and that's denoted by any capital letter. So maybe I would use T for tails, or something along those lines. But I wouldn't use S because remember we said S is going to represent a sample space. All right, sample space. All right, so rules of probability. The probability of event E, that's what P parentheses E, and notice in purple I says here, the way you would say that is P of E. So the probability of your event will always be in between 0 and 1 inclusive. So it is possible to have a 0% chance or 100% chance. That's what 1 represents. But it will always be in between them, you know, either 1, 0 or in between. It can never be greater than 1 or less than 0. Then you have when you look at your sample space, all of the outcomes in your sample space, when you look at the probabilities of each one of them and add them together, they will add up to 1. So, you know, going back to probability of heads and tails, 50%, 50%, that's 100%, or 0.5, 0.5 adds up to give you 1. You look at the probabilities of each one of them individually. Got a few more rules that have come as we go throughout the section. Those are just the first 2. So the probability model, in order for something to fit the actual probability model, it must satisfy both rules 1 and 2. So we want to verify that this is a probability model. So we have our colors. I believe we were dealing with M&Ms in this example. I just went ahead and wrote the chart, didn't need words. Color brown, yellow, red, blue, orange, and green. Then we have the probability of getting whatever those colors are. So it's 0.13, 0.14, 0.13, 0.24, 0.20, 0.16. So looking at the rules, remember if it fits the probability model, it has to satisfy both rules 1 and 2. So each probability is between 0 and 1. So we see that is the case when we look at each one of these probabilities. And then do each one of those probabilities add up to 1? That's rule 2. And the answer is yes. So we take 0.13, 14, 13, 24, 20, and 16, add them together, that will give you 1. And then the last statement, since the model satisfies, should be satisfied. Since the model satisfies rules 1 and 2, it is a probability model. Yeah, it should be cool. Since the model satisfies rules 1 and 2, it is a probability model. Any questions before we go to the next thing? So an event is impossible if the probability is 0, that means 0%. An event is a certainty if the probability is 1, that means 100%. The closer a probability is to 1, the more likely the event will occur. The closer the probability is to 0, the less likely the event will occur. All right, an unusual event is an event that has a low probability of occurring. Typically, an event with a probability less than 0.05, or in other words, 5%, is considered unusual. That's not set in stone, but that is going to be our marker for what is unusual, what's not. If something is less than 5%, that's going to be considered unusual. So don't forget that. Very good. Let's go up. Holding on for a black statement, statement of black. All right, so next we're looking at calculating probabilities. First thing we're looking at is the empirical approach. So we do the frequency of E over the number of trials of the experiment. By holding on to the statement in red. All right, so we have an example here. All right, we have an insurance agent currently insures 182 teenage drivers. Last year, 24 of them had to file a claim based on these results. What is the probability that a teenager will file a claim in a given year? All right. So if we try to find a probability that a teenager will file a claim in a given year using the empirical rule, we have totally 182 drivers, and then last year 24 of them had to file a claim. So all you would do is take the 24 and place it over the 182 if you're basing your probability off of last year's results. and you get 0.132 calculation. And so a statement that could be true for this is that for every 100 teenage drivers, we expect about 13 to have to file a claim. So where that comes from, and this, so you want to be careful with the statements and how MATLAB give you these statements. Notice they say for every 100 teenage drivers. So you take 100 and multiply it times this number here, and they give you 13.2. So that's where they get about 13 have to file a claim. So they said for every 1,000 teenage drivers, you'll multiply 1,000 by this, and that would be 132. And so it should be 132 right here. So that's how you would match that up. You make sure you get your probability and hold true to this number right here that they put in the statement. Because MATLAB will give you like 4 statements, A, B, C, D, to choose which is the right statement. So if they say 100, that means they talk about multiplying this number by 100. And then the next number right here will be, that number that you get as a result. All right, any questions before I go to the next one? So that was the empirical method. The classical method is very similar. Classical method, probability of E is the number of outcomes in your event over the number of outcomes in your sample space. And you have in parentheses, E, that's N of E, in parentheses, S is N of S. All right. So let's look at an example of flipping a coin and landing tails. You want to flip a coin and want to know what's the probability of landing tails. So first of all, we look at our sample space. Our sample space we mentioned already is heads and tails. So the number of outcomes in our sample space is 2. And when we look at our event, tails, there's only one option there, that's just tails. So the number of outcomes in the event is just 1. All right, so once you have the number of outcomes in your sample space and the number of outcomes in your event, you place the number of event over the number of sample space, and that's your probability. And for the most part, we already know that's 50% chance of landing heads, 50% chance of landing tails, but that's the thought process behind calculating. And that's the foundation of what you'll be doing, trying to find a probability of an event. All right, everybody good? Let's go alert. All right, next one, a single die is rolled. What is the probability of landing a number greater than 2? All right, so first thing we need to do is establish our sample space. So now when we talk about a die, if you ever played Monopoly or any board game that uses a die, there's 6 faces and they have these pips, what they call pips, and each one of the pips represent a number. So one pip is the number 1, 2 is the number 2, 3, and so on. So it goes 1 through 6. So when you talk about a sample space is 1 through 6. So that means we have 6 outcomes. Now, I do want to make sure we're clear on the fact that these 2 6s are 2 different numbers. They're not the same thing. If this was 1, 2, 3, 4, 5 triangle, the number of outcomes that I have is still 6. So this is the number of outcomes, and this is the list of the actual outcomes that you have. So I just want to make sure we didn't think that because that ended in 6, that this has to be 6. It could be 1, 2, 3, 4, 5, 10, but I have 6 outcomes. So that's the number of my sample space is 6. Hold on 1 second. I need to get my charger. Give me 1 second. All right, so then the number of outcomes in our event are the numbers greater than 2. So that would be 3, 4, 5, and 6. So the number of outcomes there is 4. So now that we have the number of outcomes in our event and the number of outcomes in our sample space, we place that number, the event number over the sample space number, just 4 over 6, and that'll be 2/3. All right. Questions before we go to the next one? All right. So a pair of dice is rolled. Compute the probability of rolling a 7. Compute the probability of rolling snake eyes, which is rolling a 2. All right. So first thing we're gonna do is establish our sample space, the number of our sample space first. Now, when it comes to two different dice, what we don't want to do is have to list out all of our possible combinations. Over here is giving you an idea of what we're talking about. So you're talking about you have die one and die two. If die one is one, die two is one, that's one combination. Die one is die two. Die one, die two is three, 1, 4, 1, 5, 1, 6. Then you have to do 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, and so on. So the easy way to do that is what I did here. And you can do that with any, it's called the fundamental counting principle with any type of combinations. If you have a single die that has 6 options, then another one has 6 options, you multiply those together, and that'll be 36 possible outcomes. Let's say if you had a die that had 10 faces or 10 options, and the other one had 8. 8 times 10 would be 80. So that's how that would work. Whenever you have these options and you're able to choose one out of each category, then you can multiply the number of categories together, and that'll give you the total number of possible outcomes. So the number of our sample space will be 36. 36 different ways we can roll a die, roll 2 dice and get an outcome. So then you're talking about rolling a 7. So how many different ways can you roll a 7? Die 1 being 1 and die 2 being 6. 1 plus 6 is 7. Then 2, 5. 3, 4. Now 3, 4 is different than 4, 3. It's 3 4s when die 1 is 3, die 2 is 4. 4, 3 is when die 1 is 4 and die 2 is 3. So then the same thing holds true for 5, 2 and then 6, 1. So we have 6 different ways that we could get the number 7. So once you have those two numbers, 6 over 36, going to be the probability, and that will reduce down to 1 out of 6. Any questions? Any questions? Then B says rolling snake eyes. In other words, rolling a 2. We already know the sample space is 36. Then you say how many different ways can die 1 be 1 and die 2 be 1? There's only one way. There's only one way to get a 2. And that's why it's 1 out of 36 chance. So rolling snake eyes. All right, any questions? Let's scroll up. So suppose a family asks 500 families, suppose a survey asks 500 families with 3 children to disclose the gender of their children and found that 180 of the families had 2 boys and 1 girl. A, estimate the probability of having 2 boys and 1 girl using the empirical method. And the second, write that down before we go to B. All right, and then B is compute the probability of two boys and one girl using the classical method. All right, so looking at the empirical method, there was 180 families out of 500 that said that they had two boys and one girl. So for the empirical method, all you do is take that 180, place it over 500, and that'll be the probability. So it'll be 0.36. All right. And then for the classical method, we have to do something like a tree diagram in order to establish how many outcomes we have and so on. So, I'm still copying that. So this is what we did here. So start off with the first option of having a boy first. After you have a boy, you got possibly have a boy and a girl. Then after you have a boy, you got a boy and a girl. And then after you have a girl, you can have a boy and a girl. So then you would start the tree off with a girl first. Then from that girl have boy, girl. From that boy, boy, girl. Then from that girl, boy, girl. So notice the number of our sample space is 8 possible outcomes that could occur. Change that before we go any further. All right, so then if we look at our diagram, we have 3 different scenarios in which we have 2 boys and 1 girl. It doesn't matter the order. So this one we have boy, boy, girl. This one we have boy, girl, boy. And then here, girl, boy, boy. So we have 3 different scenarios in which we have 2 boys and 1 girl. So you replace 3 over 8, and they give you 0.375 using the classical method. All right, any questions? Any questions? All right, let's see, it's 12:19. All right, so let's go ahead and do 5-2 today, because once again, I won't see you on Monday. And we will call it a day as far as lecture is concerned after 5-2. Go from there. So 5-2 is the addition rule and complements. So we have two events are disjoints. If they have no outcomes in common, that's also called mutually exclusive events. So the addition rule for disjoint events is E and F are disjoint. In other words, they don't have anything in common. If you want to find the probability of E or F occurring, you just add those two probabilities together. All right, so before we go any further, we'll make sure you're okay with the deck of cards. And just in case someone never dealt with deck cards before. We have deck of cards, standard 52 standard 52 card deck means that there are no jokers. Four suits. There are four suits: spades, clubs, diamonds, and hearts. So it's a suit talking about types of cards or category of cards. So probably you say we have spades, clubs, diamonds, and hearts. Two of them are black. Those are spades and clubs, and then two of them are red, diamonds and hearts. 13 cards each suit. We have 3 face cards and 10 regular cards. The face cards are king, queen, and jack. Regular cards, ace, and then 2 through 10. So your ace is not a face. All right. Roll them up. That's still almost black. So suppose a single card is selected from a standard 52 card deck. Compute the probability of drawing a king. Compute the probability of drawing a king, queen, or jack. Give you a chance to write it down. All right, can you scroll up? So looking at A, we want to compute the probability of drawing a king. So first thing we need to do is establish what is our sample space, the number of our sample space. Now we don't want to have to write out each single card, but we know we have 2 cards in the deck. So the total number of possibilities, the total number of cards is going to be 52. Then you say, well, how many kings? The event is to draw a king. So how many kings are there in the deck? There are 4 kings in the deck. Remember, there's 1 king for each suit, and there are 4 suits. And if that's the case, then now you can put the 4 over 52, and that's 1 over 13 when you reduce it. So that's the probability of getting a king. All right, so looking at B, we're going to compute the probability of drawing a king, queen, or jack. We're looking at B, notice the statements that I wrote. These events are mutually exclusive, so it means they are, just joint, mutually exclusive, and disjoint are the same thing. That means they do not have any cards in common. So there are no king of queens or no queens of jacks. So you have your kings, you have your queens, you have your jacks. None of them are in common. We'll see examples of things being in common in a second, but neither one of these have anything in common. So we can find the probability of each one of them individually. And it just so happens the way that cards are set up, the probability of getting a king is the same as getting a queen, the same as getting a jack, because you have 52 cards and there are 4 kings, there are 4 queens, and there are 4 jacks. But I did them individually, calculate the probability of each one individually in this example, so you see the process. So just in case you don't have it like this, you know that each time you have to calculate each one of them individually. So in each case, we have 4 over 52. So once you calculated the probability of each card individually, pulling a king, pulling a queen, or pulling a jack, now we can go ahead and add them together. So we have 4 over 52 plus 4 over 52 plus 4 over 52. That'll be 12 over 52. Now we can reduce that by 4. That'll leave us with 3 over 13 as our probability. All right, any questions? We'll go to the next one. All right. So a single die is tossed, find the probability of rolling a number less than 3 or greater than 3. We're done with the last example. Let's scroll up. All right. Give you a chance to write that. All right. So single die is tossed, find the probability of rolling a number less than 3 or greater than 3. So looking at the first probability, rolling a number less than 3. We've already talked about how single die has the number of outcomes of 6. So that's our bottom number, our sample space number. The numbers that are less than 3, when you talk about rolling a die, would just be 1 and 2. So there are only 2 outcomes that are less than 3. So the probability of rolling a number less than 3 is 2 over 6. Now, when we look at our 2 events, we have less than 3 and greater than 3. It is possibly less than 3 and greater than 3 at the same time, so there's no number that they have in common. So once again, we can just find the probabilities and add them together. So numbers that are greater than 3, 4, 5, and 6. So there are 3 numbers that are greater than 3. Probability of getting a number that's greater than 3 is 3 over 6. Once we have both of our probabilities of both of our events, we can now add them together. 2 over 6 plus 3 over 6 will give us 5 over 6. Any questions? Any questions? All right, so before we looked at the addition rule for mutually exclusive events, now we're looking at the general addition rule. This is when your events are not mutually exclusive. So that's the probability of E or F. You add the probabilities together, but then we're gonna have to subtract what they have in common. We'll see why in a second. But like I said, this piece right here, probability of E and F happening is what they have in common. So if they're mutually exclusive, this would be 0 because they don't have anything in common. That's why it wasn't included in our first formula. But generally, if they do have something in common, then we have to, do the subtraction here. Once again, I'll show you why in a second. All right, hold on a second. All right, so let's look at trying this out. We have a single dice toss. Find the probability of rolling in an even number or a number less than 5. Write down that fast, please. All right. So single dice toss, find the probability of rolling an even number or a number less than 5. So we already established that we're dealing with a die or some dice. Our sample space is 6. Now, if we're talking about even numbers, the even numbers in our sample space, that's our first event, is going to be 2, 4, and 6. So we have 3 even numbers, and that's going to be 3 over 6. That's a probability. The next event, a number less than 5. We want a number less than 5 as far as our sample space is concerned, or a single die is concerned. That's the numbers 1 through 4. So there are 4 outcomes. So that's why we have 4 over 6. Any questions so far? All right, so now these events are not mutually exclusive, they're not disjoint. So what I mean by that, that means they do have something in common. Notice they have 2 and 4 in common with both set of numbers. So if that's the case, we do have to figure out how, we see that it's 2 and 4, so we know how many numbers that they have in common. So, and that means the probability of getting a number that's even and less than 5 is 2 out of 6. But the reason why you have to subtract it in the formula is because if I were to just add this together, let me say add this and this together, that includes 2 and 4 twice. So you don't want to count what you have in common twice. So that's why we have to subtract it from the probabilities that we're adding together. So whenever you have events that are that have something in common, you do have to subtract what they have in common from the process of adding them together. So once again, we have 3 over 6, 4 over 6, and 2 over 6. And here's the formula, plugging in those values. 3 over 6 plus 4 over 6 minus 2 over 6 would be 5 over 6. Also, if you were to add just these together without the subtraction, that would be 7 over 6. And that will give us a probability that's greater than 1. Remember, our probabilities cannot be greater than 1. So that's why that has to happen as well. All right, any questions? Any questions? All right, scrolling up. So here we have a single card that's drawn from a standard 52 card deck. Compute the probability of the events of drawing a king or drawing a diamond. All right. So you want to ask yourself, are the events mutually exclusive? No, because there is such thing as a king that is a diamond. That's the king of diamonds. So they do have something in common. These events do have something in common. So we found the probability of all three pieces. So we know the sample space for each one of them is 52 because there are 52 cards in the deck. There are 4 kings, so that's 4 over 52 for drawing a king. Then you ask yourself, how many diamonds are there? Remember we said there's 13 of each suit, so there's 13 diamonds, 13 over 52. And then for the king of diamonds, there's only 1 king of diamonds, so that's 1 over 52. All right, so plug it into the formula. Probability of getting a king plus the probability of getting a diamond minus the probability of getting a king and a diamond. So it's 4 over 52 plus 13 over 52 minus 1 over 52 gives you 16 over 52. Reduced by 4s, that's 4 over 13. All right, any questions? Any questions? All right, so we have one more thing to talk about, which is the complement. Let me make sure that I have a chance to copy before I scroll all the way up. Everybody good? All right. So the complement of an event. So these are all the outcomes in the sample space that are not in the event. So we're talking about everything else. You have your event, then you have everything else. So if you want to know the probability of landing tails, the complement will be everything else not landing tails, basically heads. So when you have your event with the C superscript, that represents the complement of that event E. You know, if you had called event A, complement of event A, if you had A with the C superscript. But this C up here represents the complement of All right, complement rule. So we have three variations of the same thing. If you have the probability of your event and you want to know the probability of your complement, you just subtract the probability of your event from one. Or if you have the probability of your complement and you want to know the probability of your event, you subtract it from one. But basically, if you add the probability of your event plus the probability of your complement, they add up to one. So all of these are the same formula or same relationship, just manipulated depending on what you're trying to find or what you have. All right, so let's look at this. I think this is our last example. ACC is according, just shorthand that. So according to the National Gambling Impact Study Commission, 52% of Americans have played state lotteries. What is the probability that a randomly selected American has not played a state lottery? All right, so we want to know the probability that a randomly selected American has not played the lottery. We know the probability that American has played the lottery, which is 50%. So the probability that an American has played the lottery is 0.52 once you convert it to a decimal. Not played, you subtract that from one, which would be 0.48, or in other words, 48%. All right. Any questions on that? Any questions on anything? Let's see, that's it for that. So, any questions before we close out today? That's sections 5.1 and 5.2. Once again, next class will be Wednesday. Monday, we have a holiday. Once again, I'll open up the floor for questions, see if anybody has any. And then from there, we'll give them 5.3. All right. So, and also for the days, I'll post test two. Post test two. And like your classmate mentioned, anything I post in Math Lab, is really not due till August 5th. Just that, you don't want to wait till August 4th to get started on this stuff, right? So you want to be progressively doing this stuff as we knock it out. But any questions before we close? Any questions, any concerns? All right. Well, you guys have a great weekend. Be safe, and I will see you on Wednesday.
Have a good day.
Thanks.
Have a great weekend.
Thanks for the same. Take care.